let's do E for excellence. Okay. And okay, so we've got week 8, Monday. All right, so far we've done the Metropolis algorithm, Metropolis Hastings algorithm, and we looked at an application of the Metropolis algorithm where we used it to decipher some text, and I hope you guys thought that was kind of a neat application. If you missed Friday's lecture, check out the video, check out the code. I think it's kind of neat. So let me just write that. So far, we have done Metropolis and then the Metropolis Hastings algorithm. Okay. All right. Well, and then before we go on, why do we bother with the Metropolis algorithm or Metropolis Hastings algorithm? Why? Like, what's the whole point of this? Big picture idea? Oh, geez. Okay, hang on. Hang on. I gotta... You know what it is there's a button on the pen, and if my thumb accidentally brushes against it, it does this. Okay. Well, all right. So the big idea is that there is some target distribution, and we want to understand the target distribution, but the target distribution is too complicated for us to do it mathematically. So instead, we settle for a representative sample, right? So big idea is we have a target distribution of interest. The distribution is too complicated for direct analysis. Okay, so we settle for a representative sample instead. That's fine. Right? just to put our whole class into perspective, right? And we talked about sampling from any distribution, and our beginning half of the class prior to midterm 1 was all about, I don't know, inverse CDF and rejection sampling, and we covered ways to get a representative sample, right? So we settle for a representative sample, and so this was, things like inverse CDF and rejection sampling, and these are good ways to get representative samples, okay? But in some cases, even these methods are no good because the space is so huge that rejection sampling would become incredibly inefficient, okay? In some cases, rejection sampling or other methods are incredibly inefficient. Okay. Or you might not even have the you might not have the PDF in its normalized form, and so you can't even perform rejection sampling, okay? Other methods are incredibly inefficient, sometimes not possible, because a normalized PDF, when I say normalized PDF, I mean a PDF that integrates to one, okay? And normalized PDF is unknown, right? So you might know the PDF, but not its normalizing constant, okay? And so in those cases, some of these methods that we've learned so far are no good, right? And so it's kind of in these situations that we say, all right, let's try an MCMC method, right? Okay, so we resort to MCMC to generate a representative sample, okay? And it works. It's not MCMC. There's a lot of undesirable properties of MCMC. For example, the samples you draw are correlated with one another, right? Because you're proposing values based on your current value. So the next value you get is going to be related to the current value you have. And so, there's ways to like uncorrelate the values by either like throwing away every other one, or keeping only 1 out of 5 or something, depending on how bad the correlations are. Sometimes you've got to let it run for a long time, especially if you have a bad starting location. It has to run for a long time before it gets into kind of the zone of interest. There's all sorts of things, but in situations like this might be the only option we have, right? We have some kind of target PDF, and we can't, our math fails us, right? And so we say, okay, you know what? Let's try to get a representative sample. So we say, all right, how can we get a representative sample? And we say, all right, I've got these methods, rejection sampling, or I've got inverse CDF or whatever. Maybe those methods also fail us, okay? And then so we say, all right, let's try MCMC, where I start off at a value. I'm going to propose another value. I will accept or reject that proposed value based on, my acceptance ratio. Then we take it, and then we, move on from there, and we get this chain of values. And that's supposed to be a representative sample. And in the long run, it is. But, in the homework, you saw that depending on your proposal distribution, you can run into problems. Maybe your proposal distribution has, too little of a variance that, you're exploring your distribution space very slowly. Maybe it's too big, and so you end up rejecting all of the values you propose. Not all, but a lot of them. And so you're also exploring the space very slowly. There are a host of issues with MCMC, but it works, and we got to see an example with the deciphering where it worked in a situation where the target space was very complicated and too big to just select randomly. Okay. So far, all of the methods we've covered have been for one unknown parameter. Okay, even the deciphering one, it was one unknown parameter, which was the mapping. But so far it's been things like find the proportion of green M&Ms in the bucket, or find the proportion that the coin flips heads, or find your proportion find your rate parameter lambda, find the single mapping of letters to letters. These have all been set up where we've only had one parameter, one unknown parameter of interest to us, okay? So far, all of our methods have been for target distributions of one unknown random variable, right? And unknown is redundant. Okay, so for one random variable, okay, such as e.g., the proportion green, M&Ms, or the rate parameter lambda, or the the letter mapping. Okay, the letter mapping involves 26 letters, but it's one single mapping. Okay. So what do we do if we have multiple parameters? Okay. What can we do there? So that's what we'll look at today. We'll look at a situation where we have multiple parameters, and then we have, and we can do a Metropolis or Metropolis Hastings algorithm for multiple parameters. We can also have more efficient things. Okay. All right. So can we do? So we'll look at MCMC for distributions of multiple random variables. Okay, and so these are, we'll start off with the simplest, a simple, kind of our simplest example is basically going to be kind of 2 beta distributions, okay? So the example from the textbook example is you have 2 coins and you want to find out the joint distribution of both coins kind of proportion. Both coins kind of proportion of landing heads. Right. We could also imagine some other scenario where now I have 2 buckets of M&Ms, and one has a certain proportion green, and another one has possibly a different proportion green, and we want to know what's the proportion green in this bucket and what's the proportion green in this bucket, and we're going to make a joint distribution, okay? So, or we could have another, these are just silly examples, all right? As we have 2 buckets of M&Ms, and we want the joint distribution of kind of the proportion green in both buckets. Okay, now this is truly a silly and simplest example because in this case the 2 coins are independent. So it's the resulting joint distribution is just a product of the individual distributions, okay? And if we were to do this analytically, I mean, we already know the beta binomial model, and if we were to do something like this analytically, it's very easy. You would just kind of factor them into 2 separate beta distributions, and the joint distribution would just be the product. Okay, but again, we're going to start off with a simple illustrative example so that, and understand how the Metropolis or Metropolis Hastings and, in the future Gibbs sampler works on this simple example, and then we can make it more complicated. Okay, so these are, this. If we were given this setup, we would not normally use MCMC because we've got analytic methods that would work better. Okay, but so this is a silly example because we do have analytic methods. Okay, especially because the coins or buckets are independent, and thus the joint distribution is a pure product. But the same concepts, okay, can be generalized for non-independent situations. Okay, did everyone sign in on the attendance poll? Letter E. Generalized for other situations. Okay. Okay, so for example, you could have kind of coin 1 has, this is its from 0 to 1, this is its beta distribution, and then coin 2, I don't know, maybe you have from 0 to 1, you have something like this, and then thus the, here, actually, probably the distribution space would look something like this, if that makes sense. Where from this would be coin 2. Can you? And then on this axis is coin 1. So like if you were standing here and you were looking this way, it would kind of look like this in its profile. And then if you were standing over here and looking this way, it would look kind of like that. You have this 3-dimensional hill-ish looking thing. Okay, I mean it's simple because it's a product, and so we can picture something like this. Okay, and so so in this situation, we would have. Let me just get the. I just want to make sure the letters I'm using are the same as the book. Okay, so we have 2 parameters. Okay, the proportion of landing heads for coin 1, which we will call theta 1, and the proportion for coin 2, which we will call theta 2. Okay. And what we want, okay, is we want kind of the posterior distribution of theta 1 and theta 2 given the data, which we will just call D. So we want the posterior distribution of theta 1 and theta 2 given the data d. Our posterior distribution is a joint distribution, okay? Now, it's, in this example, our joint distribution is just a product of univariate distributions, but that is not always the case. So we're going to write it as if it were a joint distribution. So our joint posterior, I guess I can throw in the word joint, posterior joint distribution of theta 1 and theta 2 given the data. So what we want is going to be the distribution of theta 1 comma theta 2 given our data. Okay. All right, so with Bayes' rule, okay, what do we have? We're going to have the data given theta 1 comma theta 2 times the prior probability of what? Theta 1 and theta 2. And we're going to divide this by the probability of the data, right? Okay. And then, so technically the probability of data would be basically the integral of the numerator across all possible values of theta 1 and theta 2, right? So this is the integral of numerator across all possible values of theta 1 and theta 2. So I guess I'll throw the math here. Okay, so the probability of the data would be the double integral of the numerator, probability of data given theta 1 comma theta 2 times the probability of theta 1 and theta 2. There's commas in there. Over d theta 1 and d theta 2. Here, let me just slide that over. Oops, that is the wrong tool. Okay. All right, is that okay? And of course, as we've always stressed so many times, is that this denominator is just a constant. So when we do our metropolis algorithm, we don't have to worry about it. I mean, we can keep it in there. It's not a big deal. Okay, let's think about what the likelihood is, right? So the likelihood of, you know what, let's put this on the next slide, actually. All right, okay, can I flip? Still right. Okay, here we go. So, okay, so our data, we've got data from 2 coins, right? So we've got heads and tails from 2 coins. So we've got basically coin 1, and we'll have like, you know, we will have Z1 heads out of N1 flips, okay? And then for coin 2, we have Z2 heads out of N2 flips, okay? And you know, where Z1 is equal to the sum from I equals 1 to N, I guess I equals 1 to N1 of Y1 sub I, okay? Where Y1 sub I comes from Bernoulli with parameter theta 1. So, and then you get kind of the same setup, right? For you got y2, it comes from Bernoulli of theta 2, and z2 is the sum of the y2s. Okay, so our the probability of the data given theta 1 comma theta 2 is going to end up being, because we've got two independent coins, it's going to be the product of the probability of y1i given theta 1 and theta 2 times the product of the probabilities of y2i given theta 1 and theta 2. And then we realize, oh hey, you know what? y1 doesn't even depend on theta 2, and y2 doesn't even depend on theta 1, and you know this just ends up being the likelihood of Bernoulli's, okay? Of Bernoulli, and then this also a likelihood of Bernoulli. Okay, and so here we get the product of theta 1 raised to the y1i times 1 minus theta 1 raised to the n1 minus, no, not n1, sorry, getting ahead of myself, 1 minus y1i. And over here we got the product of theta 2 to the y2i times 1 minus theta 2 to the 1 minus y2i. Okay, and then with the product, this becomes theta 1 raised to the z1 times 1 minus theta 1 raised to the n1 minus z1. This is theta 2 raised to the z2, and 1 minus theta 2 raised to the n minus z2. Okay. And at this point, we recognize we kind of just have a joint distribution. This is just a product of kind of Bernoulli likelihoods, okay? Again, because our coins and our buckets and everything, Bernoulli likelihoods. Okay, so this is our likelihood, and then and we ask, okay, what is our prior distribution? Okay, so our prior distributions, this is going to be the product of, the joint distribution. So this is the prior joint distribution over theta 1, theta 2. This is going to be basically a beta distribution with shape parameters A1 and B1, and times a beta distribution with shape parameters A2 and B2. Okay, so maybe I'll write beta distribution times beta distribution, because they're independent. All right. So anyway, we do all of this, and we get. So this is theta to the A1 minus 1 times 1 minus theta to the B1 minus 1, and this is theta 1, and this is theta 2 to the A2 minus 1 times 1 minus theta 2 to the B2 minus 1. Okay. And then, all right, so our posterior distribution, this is okay. I mean, I did this quickly, but it's just a product of betas, right? So our posterior joint distribution is going to be equal to the data given theta 1, the likelihood, times the prior, divided by some constant. So I will just say it is proportional to this, and let me just go back to our previous slide. Week 8, Monday, this is the one we want. Okay, and we'll just copy this. It's taking, where is it? Okay, week 8, Monday, slide 5, that's the one I want. Okay, so it's going to be this times this. Okay. Wait. No, that's the wrong thing. Where'd it go? Oh, shoot. I want this thing. Is this not gonna work? Okay, so I want that. Copy. Paste. Okay, there we go. All right, so we multiply these together. Okay, so anyway, gosh, this is a pain in the butt. Okay, so we got theta 1 to the z1 plus a1 minus 1 times 1 minus theta 1 to the all of these things together. What is that? n1 minus z1 plus b1 minus 1. All right, anyway, just add all the exponents together. You guys get the idea. z2 plus a2 minus 1 and 1 minus theta 2 to the n2 minus z2 plus b2 minus 1. All right, no big deal, right? Okay, and then so we say this is proportional to this, and then we can say, okay, now we've got a beta distribution with parameters z1 plus a1, comma n1 minus z1 plus b1 times a beta distribution with z2 plus a2, comma n2 minus z2 plus b2. Oh gosh, all right, we did it. Is that okay? All right, so this is, we could do this via formal analysis, and because it's a product, it's easy. But again, pretend we're in a situation where it's difficult. Maybe to do something like this. Okay, so how would Metropolis Hastings work in a situation like this, or the Metropolis algorithm, because I'll end up using a symmetric proposal distribution. Okay, what would be an appropriate proposal distribution? So let's think of, okay, how do we do Metropolis algorithm for a multivariate distribution? So how does Metropolis algorithm work? We just start at an arbitrary, right? Start at an arbitrary location. So we would have kind of the coordinate theta 1 comma theta 2. And then what would we do? We propose a new coordinate. And do we have, is there notation for this? We propose a new coordinate, which would be what? Theta, I guess theta 1 prime comma theta 2 prime. And these come from some kind of proposal distribution, right? So what would an appropriate proposal distribution be? So the proposal distribution needs to be a multivariate distribution, okay? Okay, so some examples could be multivariate normal. And so we could say theta 1 prime and theta 2 prime will come from a two-dimensional normal distribution, and the mean would be what? Our current values of theta 1 and theta 2, and maybe the standard deviation will be the two-dimensional identity matrix or something like that. Okay, so that could work. Or multiplied maybe by some scaling thing. Okay, so maybe you don't have variance 1, but a smaller variance or a bigger variance depending on the situation. So that could work. Okay, I mean you could even choose to have a standard deviation that has correlation in it if you want to propose kind of from an ellipsoid rather than a circle. That's fine. All right. What else? What would a uniform proposal distribution look like? Okay. So you could have a uniform, basically a 2D uniform distribution, and we would say what? Theta 1 prime and theta 2 prime come from basically I don't know what the notation for this would be, but basically it's going to be the joint distribution of a uniform going from your current theta 1 minus 1 to theta 2 plus 1, theta 1 plus 1, and joint with theta 2 minus 1 to theta 2 plus 1, or something like that. Okay. So you're centered, you center at your current location, theta 1, theta 2, and then you say, all right, I'm going to draw a square with sides of length 2, or maybe smaller sides or bigger sides. And we're going to say we're going to just randomly pick a point inside this square. Okay. And then I'm sure you can think of other proposal distributions. These are just simple examples, right? And then, and then what do you think the next step in the metropolis algorithm would be? So you have your new proposed location. So we have proposed location, theta 1 prime and theta 2 prime, and then what do we do? So we calculate our acceptance probability. And what do you think our acceptance probability is going to be? It's exactly what you think. if you know the Metropolis algorithm, it's going to be exactly that. It's going to be the minimum between what? 1 and probability of your proposed value divided by probability of your current value. Exactly, right? And then, if it's Metropolis Hastings, maybe you have kind of the ratio of kind of the imbalance ratio for the proposal imbalance ratio to offset that. Okay, so you accept this, and then what? And then you draw a random uniform to decide whether you accept or not, and then you move or not, right? So then you draw a random uniform, draw U to decide whether to move or not. Okay, and that's it. That's the Metropolis algorithm. So this doesn't seem like a big deal, right? This seems like, oh yeah, this works. And especially when you have a whatever it is that you're going for, you have this thing. Okay, so this probability of the proposed divided by probability of the current, especially if we're in a Bayesian situation, we don't have to calculate the normalizing constant in the bottom, right? So we do not need the normalizing constant probability of the data to get this ratio. So if you figure out the numerator, which is going to be the product of the likelihood and the prior, you don't have to worry about figuring out that denominator, which is a huge help. Okay. I got 2 minutes. We run into issues with the Metropolis algorithm, or even with the Metropolis Hastings algorithm, in higher dimensional contexts, okay? So you could imagine as we have higher dimensions, right? So in one dimension, you would be centered at your current value, and you'd go either, you'd pick a value, within some span here, okay? And then when it's 2 dimensions, so just imagine kind of the uniform case, you'd pick a value between, +1 or -1, okay? And then now in the uniform case, if we go into 2 dimensions, now we're picking a random point within a square, okay? And if we go to 3 dimensions, we've got a cube, and we're picking a random point in a cube. And then, in higher dimensional spaces, you're picking a point in some hypercube. And what happens is we run into the same problem where the value we propose will get accepted with less and less and less frequency. Because, in 1 dimension, either the value you proposed was good or bad, okay? Now, in 2 dimensions, you might propose for one of the variables is like a likely value to be accepted, but the other variable is unlikely. So that coordinate will be rejected, okay? And then in like 7 dimensions, if any one of those values is really unlikely, then the whole, coordinate of 7 points, or 7 coordinates will get rejected, right? You could get lucky and get like 6 are good, but if that 7th one is unlikely, just from bad luck in the proposing, that whole coordinate of 7 things is going to get rejected. And so we run into issues where our proposal distributions become less and less successful, okay? They might be good proposal distributions, but they're less and less successful because of this problem of high dimensionality, and it's a lot harder to hit a target when you've got a whole bunch of the target exists in many dimensions, right? So.
Do we shrink the parameters then?
So you can shrink it down. You can shrink down your parameter so you're in a smaller space, but that still doesn't get rid of the problem because now you're like exploring super slowly, okay? And depending on what your target distribution looks like, if your target distribution is kind of like this oblong football-looking thing in three-dimensional space, and you say, all right, in order to accommodate this, we've got to shrink down our proposal. You're going to be exploring that space very slowly. And so we've got all sorts of problems. So we need a more efficient system, okay? And we'll take a look at that on Wednesday, and that's going to be Gibbs sampling, okay? So this is what we've got, and then, yeah, so we'll see that on Wednesday. Okay.